Hello, welcome back to the second course in physics. In this lecture and the few lectures to come, we will be talking about a different topic which is related to magnetic phenomena, the topic of magnetostatics specifically. In this particular lecture, we will be talking about magnetic fields and magnetic effects. And the contents of this lecture will include some general introduction, and then we will define the magnetic field in vacuum. We will discuss the magnetic force on moving charges. We will encounter the Lorentz force, the Hall effect, which are based on magnetic forces acting on moving charges. And then we will discuss the concept of magnetic field lines. We will also encounter the problem of the force exerted on a current carrying conductor by a magnetic field. Under that umbrella, we will consider the force acting on a straight wire carrying current, and then we will consider the case of the force acting on a current loop, a closed current loop. And finally, we will talk about the torque, the rotational torque acting on a current loop in the presence of a magnetic field. And at the outset of this lecture, we would like to mention some historical facts, and we start by saying that the Chinese have known the magnetic phenomena and magnetic effects a long time ago, and that's around probably 2637 BC. So ancient Chinese knew magnetic phenomena, and magnetic forces were observed between naturally magnetized minerals and materials, rocks. So these effects were observed a long time ago. The mineral magnetite, which is one type of the iron oxide, Fe3O4, was found in Magnesia in Ionian Greece in 1640 BC. This is a natural rock which has the property of attracting metallic iron pieces. And later on, the use of a magnetized needle, or a piece that has magnetic properties, magnetized, it was used as a compass needle around the year 1000 AD, possibly by the Chinese or the Arabs, who have used this compass as an application of the magnetic materials in their navigation systems. Now we start talking about the magnetic field, and we consider the magnetic fields in vacuum. We will not be dealing with the effects of magnetic fields in materials in this discussion of ours. We have to remember that charges, electrical charges, set up an electric field around the charge distribution. And similarly, a magnet or a magnetized piece would set up some effect, magnetic effect, which is manifested by a magnetic field B in the region close to the magnets, just in a similar way. Thus, we have seen previously that an electric charge existing somewhere in space would lead to the presence of an electric field in the space around it. Now, since we see also magnetic effects, magnetic force effects around a magnetized piece, the question arises, would magnetic charges exist and lead to the onset of a magnetic field in space? Is that question valid? Do we have magnetic charges in the same way that we have electric charges that introduce electric field? Experimentally, magnetic charges or magnetic monopoles, just like the positive and negative electric charges that we have discussed, have never been seen. So although theoretically the magnetic charges are proposed and hypothetically they were assumed to be there, but they have never been seen experimentally. Now, if we have a bar magnet or a piece that is magnetized and it consists of the two poles always, we don't have a single pole, we don't have monopoles, at least until now. If a bar magnet is free to rotate, if it's left free with no forces acting on it, then one end of it will point north, towards the north, the geographical north. And this end of the bar magnet that points always towards the north, if it is free to rotate horizontally, in a horizontal plane, that end is called the north pole or the N pole of the magnet. The other end of the bar magnet, which would be directed towards the geographical south, is called the south pole or the S pole of the magnet. So each bar magnet, it has, instead of talking about magnetic charges, like in the case of electrostatics, we talk about positive charges and negative charges. In terms of magnetism, we talk about north pole and south pole. The north pole, which is somehow equivalent to charges in a way, the north pole is the one that always points towards the geographical north if the bar magnet is left free to rotate. And this is what we have. If this is Earth, and this is the geographical north, and this is the geographical south, if we have a bar magnet that is free to rotate, then always one end of it would point towards the geographical north, and it's called the N pole, and this other pole is called the S pole. Now, just like electric charges, the magnets interact and they exert forces on each other. And we observe similar effect to the electrostatics, to the case of electrostatics, where we see sometimes the interaction of magnetic objects or magnetized objects. We see that the forces are sometimes attractive, and sometimes the forces are repulsive forces. And experience shows that if we have opposite poles near each other, opposite poles attract each other. They always attract each other, just like in electrical charges or electrostatics, that opposite sign charges, they attract each other. So an N pole near an S pole would attract each other, S pole near an N pole would attract each other, and yet similar poles repel each other. So if we put the S pole opposite or next to the S pole, they would repel, and similarly, N pole next to the N pole, they would also repel. So forces are either repulsive or attractive, and this is similar to the case of electrostatics too. According to experience and experiments, it is easy to conclude that Earth is a huge magnet. Because a magnetized bar, if it is free to rotate on the surface of Earth, it always points towards the northern pole, one piece of it, one end of it, and the other end towards the south. That means the Earth has some sort of a field that affects the bar magnet. Otherwise, the bar magnet will not be able to rotate. In order to move it, you have to exert force on it. And thus, we conclude that Earth can be viewed as a magnet. And the south magnetic pole of Earth is near the geographical north pole of Earth, near the Arctic. And that is because, simply as we mentioned, because dissimilar poles they attract, and similar poles repel. So if the N pole of a bar magnet is directed towards the geographical north, that means the geographical north should be a south earth pole. It should be a south pole of the Earth magnet itself. So this is how it looks like if Earth is this globe. This is the geographical north, and this is the geographical south. And if we view it as a magnet, then the S magnetic pole is near the N, the northern geographical pole, near the Arctic. How are magnetic fields produced in space? How can we produce magnetic fields? Magnetic fields in space are set up either by moving electrical charges. Moving electrical charges are simply currents. So the current produces magnetic field in space, and that is the case of what we call electromagnets. Electromagnets are devices by which we can produce magnetic field by the effect of running current in wires. And also, we can set up magnetic fields in space by the effect of some special particles, elementary particles. Elementary particles naturally, by existence, have magnetic moments, or they are some sort of like small, tiny, magnetized materials. And the large aggregates of these elementary particles, which make up the objects, they can produce a macroscopic phenomenon, macroscopic magnetic phenomenon in space. So we can set up magnetic fields in space by elementary particles, which constitute objects like permanent magnets, the permanent magnets that we use in our everyday life. Now we come to discuss the magnetic force on a moving charge, and we are concerned with the following question. If we have a magnetic field in space and we have a moving charge in space, of course, if we have a magnetic field and we have a stationary charge, the magnetic field will not exert any force on that charge, and that can be seen by experience. Just have a magnetic bar in front of you and put a charge in its field, it will not be affected. However, if that charge is moving in space where there is a magnetic field, then the motion of the particle will be seen to change due to the presence of the magnetic field, which means that the magnetic field exerts force on the moving charges. And the magnetic field is defined accordingly in terms of the force that it exerts on a moving charge. This force that it exerts on moving charges can be used in order to measure and define the magnetic field itself. Now, experimentally, it has been seen by doing some experiments that the force of a magnetic field on a moving charge, if the charge is q and it is moving in space with a velocity v vector, that has both magnitude and direction, the force that a magnetic field in that region that exerts on the charge is simply equals to the charge q times the velocity v of the charge cross b, the magnetic field vector. And that means that if the charge is positive, then the direction of the magnetic force on the moving charge is in the same direction of v cross b. And that direction can be obtained from the by using the right-hand rule. If we point in the direction of v and then turn our fingers to the direction of b, from v to b to the direction of b, then this would be the direction of v cross b, as we have discussed in previous lectures. This is the right-hand rule. So this is the magnitude, and the magnitude is qv b sine theta, according to the definition of cross product, and the direction is in the direction determined by the right-hand rule. This field, the so-called magnetic field, is known as the magnetic induction. There are other fields that define the magnetic field, but this particular one is called the magnetic induction. Now, we have mentioned that the magnetic field in space would exert force on a moving charge. How would a charge move? What is the track of the charge as it moves in a magnetic field? A charge moves like this in a magnetic field. So if, for example, if the particle is not charged, then once it enters the magnetic field, it remains at the same path. So it's not influenced by any force, an uncharged particle. However, a positive charge would be drifted upward if the magnetic field is going into the page. These crosses mean that the magnetic field is directed inward into the page. So the positive charge, the direction of the force acting on a positive charge is in the same direction of v cross b, which would be upward. Upward, that means it will shift or it will drift the path of the positive charge upward, and vice versa. If the charge is negative, then the force acting on it will be in the opposite direction of v cross b. That means it will be directed downward, and the negative charge will be drifted below. So this will be the path of a negative charge. This will be the path of a positive charge, and a neutral charge with no a neutral body with no charge would remain moving in a straight line as it enters the field of the magnetic influence. The units of the magnetic field can be derived from the definition of the magnetic field, as we have seen. So in the international unit, the international unit for the field is the force divided by charge divided by velocity. So the unit of B should be Newton per coulomb per meter per second. But Coulomb per second is simply the ampere, as we have mentioned before. So the units of B is Newton per ampere meter. And this is the international system of units. This unit is called the Tesla. So 1 Tesla is equal to 1 Newton per ampere meter. This is the SI unit of magnetic field. However, this unit was not used until recently, and an older unit was still in use because the Tesla is a huge, is a very strong field actually. So another unit that is still in use is the Gauss, which is much more attainable in everyday life. And the Gauss is related to the Tesla as 1 Tesla is equal to 10,000 Gauss, 10 to the 4, or 10,000 Gauss. So this unit is smaller than the Tesla. Tesla is a very large quantity in magnetic strength. And examples of fields, for example, the Earth's magnetic field at the surface of Earth is 1/100th of a Tesla, 10 to the minus 2 of a Tesla. The magnetic field near a big electromagnet, a large electromagnet, is simply 1.5 Tesla. And that shows that the Tesla is a very huge amount in terms of strength of magnetic field. And near a small bar magnet, the magnetic field induction is around 10 to the minus 4 Tesla. Very, very small. So that shows that the Gauss is sometimes a useful unit for measuring the magnetic fields. Now we talk about the forces, and we recall that forces acting on charges are not only electrical, they can be also magnetic. So if we have a charge that is moving in space, and in that space if there is both magnetic field and electric field, then the charge will experience force from the electric field, which is the electrostatic force, and from the magnetic field, which is the magnetic force. And the combination of these forces is called the Lorentz force. And the Lorentz force, accordingly, is the combination of the electrostatic force, which is Q times the electric field, plus QV cross B. This is the magnetic field. The combination of these forces is called Lorentz force. And we have to take care of the directions, of course, in adding these two terms. The use of this formula by J.J. Thomson in 1897 led to a very, very important discovery in the history of physics, which is the discovery of the electron. The Thomson used this formula to the results of his experiments using Lorentz force led him to believe that there must be another particle that is different than the other known particles, and that particle is the electron. So this led to the very famous discovery of the electron. And that's why we take into consideration this particular experiment. Thomson used the null method for crossed electric and magnetic fields. The device which uses this null method is called the velocity selector to evaluate the ratio E over m for the electron. And the principle of this experiment by which E over m was determined is the following. We have this device which is called the velocity selector. We have an electric field applied between the two plates, since the two plates are charged positive in the lower part and negative in the upper part. So this electric field influences the electrons with an electrostatic force that is directed towards directed below, and the existence of the magnetic field. Here, the magnetic field with dots, that means it is emerging from the page. The electric field is directed upward from the page, and this influences the electrons by a force that is directed upward. So the electrons, as they move in the region of the velocity selector, or between these two plates, where there is an electric field and a magnetic field, and these two fields are perpendicular to each other, as we see, then there are two forces acting on the electron as it moves inside or between these two plates. So the electric field and magnetic field are changed or tuned until they are equal, and when they are equal, then the electron will emerge from between the two plates. Otherwise, if one of them is bigger than the other, if the magnetic field force is bigger, then the electron will be deflected upward and it will hit the upper plate. And if the electric field is higher, then the electron will go downward and it will hit the lower plate. But if the electric field and the magnetic field are right, such that the total force is 0, this is the null method, then the electron will keep going until it emerges from between the two plates, and then it travels in the field of the magnetic field. It travels with this velocity by which it emerges from between the plates, and because of the nature of the magnetic force, QV cross B, the force is always lateral, is always perpendicular to the velocity direction, which will make the path to be a circular path. So the electron will go through a circular path in the magnetic field. That is due to the fact that the magnetic force is always normal or perpendicular to the direction of the velocity. And this is the basic principle, and here we start discussing the relations by which we evaluate E over M, and from the equivalence of the two electric and magnetic forces, we obtain the velocity of the particle as it emerges from the velocity selector should be E over B. So by changing E and B until the forces are equal, and until we see an electron emerging from between the plates, then E over B is the velocity. So that way we know the velocity of the particle that is emerging from the selector, from the velocity selector. That's why we call it velocity selector, because setting E and B will give you the right velocity. And from the circular path, from the motion of the electron as it emerges from the velocity selector, which forms a circular path, the circular path means that there's a centripetal force acting on it, and the centripetal force mv square over r is equal to the net force acting on it. And in that field, the net force is only the magnetic force, which is the charge of the electron, which is E times the velocity times B. And the velocity is known here. It is E over B simply. So thus, just putting these together and modifying, we obtain the value E over M is equal to V over RB, which is equal to E over RB square, where R here is the radius of the circular path in the magnetic field region. So E over M is determined by measuring the circular radius and the electric field applied and the magnetic field applied. And now let's discuss another effect which arises from the magnetic forces acting on charged particles moving in the field, the Hall effect. we have seen that the charges moving in space are influenced by a magnetic force. Now, the question is, if we have electrons that are drifting in a conductor, are these electrons affected, or could they be deflected by the application of a magnetic field? That question, the answer to that question is yes. If there are electrons drifting in a conductor and we apply a magnetic field, the electrons will drift, will be influenced by a magnetic force, and will drift in the same way that they are drifting in empty space. And Edwin Hall in 1879 has demonstrated that this effect can happen. And this effect, analyzing all the equations and the parameters included in this effect would allow us to find out the sign of the charges that carry or transport the current in a conductor. So when we talk about current, we say, what are the carriers of current? Are they the positive ions? Are they the negative ions? Are they the holes? Whatever. So this Hall effect can allow us to answer these questions. And also, Hall effect is an experiment by which we can measure the number density of these carriers per unit volume. So some important conclusions about the transport properties of matter can be obtained by this experiment. In order to explain Hall effect and how it works and how can we use the results of Hall effect for the various applications, we consider a strip of metal. And for the time being, let's consider that this strip of metal is parallelepiped, where it's like rectangular in each side. And the dimensions of the rectangles are not necessarily the same. So let's assume that in one dimension it is A, the length of the strip is A, the width of the strip is B, and the height of the strip is D. And let's assume that this strip is carrying a current I from right to left, as shown in the figure. It carries a current I. That means the electrons are drifting left, towards the right, I mean. The direction of the movement of the electrons is in opposite direction to the direction of the conventional current. And let's assume that a magnetic field that points into the paper, into the page, is applied to the strip. And we mentioned that as the current is moving, or the charges, the electronic charges are moving in the field, there is a drift of these charges due to the magnetic forces acting on them. So the negative charges will be drifting towards the lower or the bottom side of the strip. So the negative charges will accumulate on the bottom side, as shown here, and thus a residual positive charge will be residing on the upper side of the strip. And this process keeps going until building a potential difference between the upper and lower part, until equilibrium is maintained. At equilibrium, when there is no more drifting of the charges, the potential difference between the upper the top part and the bottom part of the strip is called hole voltage. So hole voltage V sub H is equal to E, the electric field between the upper part and the lower part, times the height of the strip, which is D. ED is equal to V hole. Also, now from Lorentz force is 0 acting in equilibrium situation. Lorentz force is equal to 0. From Lorentz force, that means the electron, as it is moving in the strip, the magnetic charge and the electric charge due to hole voltage are equal and opposite in direction, of course. So that means we have equilibrium situation and the current keeps going without any more drifting. So the electronic charge times the electric field set up by hole voltage, by this drifting phenomenon, in equilibrium should equal to the magnetic charge affecting the electrons as they move in the strip, E times V times B. And this also is coupled with the relation for the drift velocity as we have derived previously. The drift velocity V is equal to I over the number density of the charge carriers times the charge per carrier times the cross-sectional area. And the cross-sectional area is D times B, the height times the width of the strip. And that gives the drift velocity is I is equal to N over EdB. And thus, combining all these things, we get E over B is equal to I over NEdB. And then the hole voltage is related to the electric field, which we have just derived. The hole voltage is then equal to B I over NEB. This is derived from the previous equation. And if we define now the quantity 1 over NE, and we call it hole constant, R sub H. This constant gives the value of the number density N of charge carriers in the material. So thus, analysis of this experiment and the determination of hole constant gives the number density, and the type of carriers in the conductor is determined from knowledge of which side, whether the upper or the lower side of the strip of metal is at a higher potential. And now the magnetic field lines are introduced as a concept, just like in the case of the electrostatic case. And we mention here that the direction of the tangent to the field lines at any point is the direction of the magnetic field at that point, just like the case of electrostatics. And the condition, this condition or this statement is written mathematically in the form of B cross dr is equal to 0. Again, this is reminiscent of the electrostatic case. And the just also as in the electrostatic case, the field induction is stronger where the lines are closer to each other, and vice versa. The magnetic field lines are closed. They are not like in the case of electrostatics. They emerge from the N pole of a magnetized piece, and they enter the magnetized piece at the S pole. So, for example, if we have a bar magnet, a simple bar magnet, they start from N pole and end in the S pole, and inside the magnet, they go from the S to the N back, forming a closed loop. And this is another shape of a magnet. Again, the lines, they start from the N pole and they end in the S pole, and this is a third shape of known magnets. And the field lines, they enter from the N pole, which is the upper pole in this case, going towards the S pole outside in the gap. And now we move to discuss the force, the magnetic force on a current, because we know that the magnetic force, the magnetic field exerts a force on a moving charge. And since the current is a moving charge, then we can anticipate that the presence of a conductor carrying a current in the presence of a magnetic field should experience a magnetic force. And we can calculate this magnetic force as follows. We can imagine that we have an element of length of the conductor carrying the current, and we can calculate what's the charge inside that element of length, which is dl. The charge dqn in that element times the velocity, in this case the drift velocity of charges, which is v cross b, that is the force, the magnetic force exerted on this element of length of the charge carrier. And that is simply equals to dq times dl over dt, that's what the drift velocity is, dl by dt, cross b, the magnetic induction. And that is simply equals df, the magnetic force is equal on the element of length, is equal I dl cross b, since dq by dt is simply I. And in order to evaluate the total force exerted on that whole conductor, it is simply we have to integrate over this quantity. And for example, if we have a straight conductor of length L carrying current I in a constant magnetic field, the force is simply I times the length of the conductor cross the magnetic field. And if we consider now the magnetic force on a loop, the loop experiences no magnetic force, because simply the integral over dl is equal to 0, and thus the net force is equal to 0 on the loop. That means the loop does not translate in the magnetic field. However, because the forces acting on the different sides of the loop are acting on different directions and at different points, so they exert rotational effect on the loop. So a loop existing in the magnetic field, as shown in this figure, would rotate in the magnetic field. And for a rectangular loop of length A and width B, the forces on the sides of the loop, F1 is equal to F2 and is equal to I times the length of the string A times the magnetic induction B. And the torque is rotational effect on the first side, IAB times B over 2, plus IAB times B over 2 from the other side of the loop. And that gives a total torque of I times A times B times the magnetic induction, which is the current times the area of the loop times the magnetic induction. And if the loop consists of n turns, then the total torque is equal to n times this quantity, Ni times the area of the loop times the magnetic induction, which is simply mu times the magnetic induction, where mu is the magnetic dipole moment of the loop. At this point, I would like to end my lecture and thank you for your attention.